All right, this is our Stirling demo. My name is Ian McNeil.
My name is Julia Engebretson, and for reference, this is our clicker. I'm not texting the whole time. It's how we change sides.
Glad that worked.
So what is a Stirling engine? A Stirling engine is a device that utilizes the Stirling cycle in order to produce work. This was a revolutionary device due to its high efficiency and environmentally friendly nature. Given that the machine is a closed system, there are no emissions such as exhaust that would be produced by similar devices such as a diesel engine. Furthermore, the device only requires a heat source to operate, which can be produced from a variety of different sources such as solar power. Finally, an added bonus to this engine is that it is very quiet. Given the absence of combustion or similar explosion, the engine is very discreet while it runs. This not only benefits those looking for the luxury of a quiet power source, such as yacht owners, but for those seeking a more tactical approach to silence, such as military submarines.
All right, I'm going to give you guys a brief history of the Stirling engine. So the Stirling engine was invented in 1816 by Robert Stirling, and his main patent actually focused on he called the heat economizer, which is basically just like one of the first heat exchangers, and it was used in the Stirling engine to take heat from one side to the other, so transfer from the hot side to the cold side. And he also really detailed his closed system design, so like it was a closed air which is then heated. And then he came out with a few more patents. So in 1927, he patented what you see today as the Stirling engine. And he originally invented it as a rival to the steam engine because he saw the inefficiencies. They were like running at like 10% at the time, and he thought he could improve that efficiency. So, and it did prove to be much more efficient. However, they were expensive to build, and it wasn't as powerful. They were really heavy, and it didn't produce as much power as a steam engine. So it was first used to pump water out of a quarry, but eventually one of the attendees of the engine forgot to replace one of the parts, and the whole thing burnt down. So it's kind of sad. And then, about like in the 1970s, NASA and automotive industries started looking into the Stirling engine to replace car engines because they saw that ideally it should have more efficiency, but they, due to its low power to weight ratio, it wasn't really practical in cars because it just would weigh the car down. So even though it was more efficient, you ended up averaging about the same. And automotive industries just didn't want to pick it up because they were like, what we have now is working fine. We don't need any change. And it wasn't that much better. So, but ideally today they should be able to get it a little more powerful, but that's a today problem.
So at its core, it converts a temperature difference into mechanical energy. Gas is sealed in a closed system, which we will be referring to as the working fluid of the cycle.
And then heat is added to that closed system, so basically the gas is heated up, and then as that gas expands and contracts, it powers the piston, and that's where you get the work coming through. That's where you get the work from in the Stirling cycle. And so most of the work is transferred to mechanical work, and then to use to spin a wheel, and then the momentum in that wheel is used to keep that cycle going.
And we have a little animation of a simple Stirling device. So as we can see, the heat source is causing the air to expand and contract, and compression and expansion, which is being turned into mechanical work, which is driving the wheel.
All right. So some terms you may not have heard before that are crucial to understanding our next steps of how the Stirling cycle really works. So the power piston basically is used to compress and decompress the gas, so it changes the volume. And this is essentially how the work is provided through the engine. And then the displacer is on the other side of that piston, and it's basically used to move the air from one side to the other. So the air gets really hot, and then the displacer moves it to the cold side, it cools down, and then that helps drive the piston.
So then the regenerator, which is also going to be used interchangeably with the term heat exchanger. It's the heat source that is internal to the engine, and it's where some of the heat is recaptured. So that's going to be denoted as like QR. So it's not Q in and it's not Q out because it stays within the system and is constantly being reused. And this is why when we take away the heat source from the device, it's still able to like run independently for a little while.
And ideally in the cycle there, you have, so like the heat exchanger loses a little bit of heat, and that's where your loss comes from. But it actually does a pretty good job of retaining it. That's why it's more efficient than the other engines. All right, so modeling the Stirling cycle. So on the left here, you have your simple Stirling cycle model. It starting in step 1, you have from process 1 to 2, you have isothermal compression. So basically, it's at a constant temperature, and it takes a little bit of momentum from as the cycle is going, the wheel has momentum, and that's used to compress in that first step. But to get it started, and you'll see when we demonstrate, you kind of just have to give it a little push to get it going. So from 1 to 2, it's compressed, so the volume decreases, the pressure increases. And then from 2 to 3, it's heated inside that gas, and that's that Q in is used to heat it. So the volume stays the same, but the pressure keeps building and building. And then from 3 to 4, you have isothermal expansion. So it's the volume's allowed to increase, the pressure is going to decrease, but again, the temperature is going to stay the same. And then from 4 to 1, you have Q out. So you have the air is now on the cool side, it's cooling down. And Julie, do you have anything to add to that?
So just to be clear, so this is when we're actually lighting it first. So this is the external Q in and the external Q out. And then this is like within the system. So this is going to be our QR. So when it's this Q out is going to go to the regenerator or the heat exchanger, and then this heat is coming in like we said by the regenerator or heat exchanger again.
All right, so the first process in the Stirling engine cycle is constant temperature compression, so that isothermal compression. So basically I know I kind of touched on it in the first slide there, but gas is compressed as work in, usually from the wheel. It's usually momentum. It compresses that piston, which so the volume is going to decrease, the pressure increases, and then the displacer, the gas is going to move the displacer, so the gas is going to move from what was the cold side to now the hot side, where in the next phase it'll be heated up. So process 2 to 3 is just the constant volume heat addition. So it's held in place by that. It's basically just heated up, and as it's heated up, the pressure is increasing, but the volume stays the same. So then it's building and building, so that eventually it's going to expand.
So this is the isothermal expansion. So the temperature is remaining constant through the external Q in, which is going to be from our external heat source, which is we're going to see like a little flame that we have. So at state 3, the working fluid has reached a maximum pressure, a maximum temperature, and a minimum volume. So this is probably the most important process, just because this is where we're going to see the overall positive work out of the cycle, which is going to be our mechanical work. And this is because the work out of the cycle is much larger than the work in, which is what we use to initially compress it. And then what we can see the device doing during this process is the piston will begin to move towards the outer rim of the cylinder as it expands. And then we're going to go to the next process. So this is our isovolumetric heat rejection. So this is the piston's going to be fixed, so there's no change in volume. But during this process, the heat within the working fluid is rejected and is moved to the regenerator, and that's going to be our QR because it doesn't leave the system entirely. So temperature of the working fluid will decrease to T3, and then what we're going to see the device actually do is, so like I said, the piston is fixed. The displacer is what we call a regenerator matrix because it's what's taking the heat out, and it moves so that it's forcing this high temperature working fluid to pass through it, and it's going to exit at a lower temperature.